তাড়াতাড়ি ছেড়ে দিই, চল। হ্যাঁ, চল চল, দেখি চলে।
You please calculate the Jacobian and check that what are the eigenvalues. Okay, the Jacobian, that is what I think we can expect mu minus 1 mu. That is the Jacobian, that is we should get. Please check whether by that time that is I convert into the polar form. Once you find the Jacobian, then that is we can write this one, right? That is most probably that is you will find for mu greater than 0, it will be an unstable focus, and for mu less than 0, it will be a stable focus. Most probably. Please check that is what is the Jacobian, and then what are the eigenvalues. It would be of course a complex conjugate eigenvalue. try to analyze first by yourself, okay? Then I will explain. I have done all the derivation and the hints also, that is how to analyze the stability and limit cycle, everything I have written. So you check everything, okay? These two, right? This one r dot minus mu r plus r cube, that is equals to this into tan theta. And here also in the 6 you have the same expression, that is if you switch this sin theta to this side.
So we are dividing the equations.
Not dividing, like this one is equals to this cos theta. So tan theta. And from this one also the same expression is equals to minus of r this into cot theta. So from that's why I have written this. Is it now fine? So for the same left hand side, the right hand side should also be equal. That is the logic. Are you able to follow?
If theta dot equals 1,
Huh.
that implies theta t equals t.
Oh, yes, great. That is theta dot equals to, that means rate of change is constant. Like you shouldn't like theta dot equal constant. Sorry. The logic is that is when you have suppose either logarithmic spiral, I mean in case of stable focus, unstable focus, or periodic orbit, if there has to be any sustained oscillation or even damped oscillation, there must be a theta, right? And especially in the limit cycle means sustained oscillation. So in some cases, if you find that the theta dot is coming to be constant, that means the omega angular velocity that is constant, then definitely like there is a chance of limit cycle, but we cannot immediately say whether the limit cycle will exist or not. But if there is theta dot equals to constant, that means there will be continuously a change of phase, then it is for sure, or not for sure, at least there is a high chance that is a limit cycle can appear. Now you have to check that theoretically there are criteria like the Poincare-Bendixson theorem and then the Bendixson's criteria that we will learn after the mid-sem. So theoretical framework is already there, but from this solution also that we can apply our equation in terms of this theta as well as r to check whether there is a limit cycle. Okay, that we are going to discuss. So here there is I wanted to write not theta, that is correct. If we take the integration, then theta equals to t plus c. But here anyway there is theta dot constant. So that means it is continuously change of phase, right? As if that is you have a phasor and that phasor is continuously rotating. Whenever you like write a periodic orbit, like a sin omega t plus theta or a sin omega t plus something, right? So omega, if omega equals to 0, then definitely it is not a periodic orbit, right? Whenever you get a periodic motion, there must be a non-zero omega. That is the thing I wanted to mean. So here this theta dot is nothing but omega. Okay? In that sense, now from this r dot equals to 0 will give you 2 points, either r star equals to 0 or plus minus root u. right? We analyze the stability with respect to the r coordinate later, okay? That is, I am not doing that is all together because then it may be confusing to you. So let us first find the Jacobian. I hope you have already found the Jacobian. What you are getting? I hope the same thing, mu minus 1, 1 mu, right? Mu minus 1, 1 mu. Then what is the expression for the lambda? I hope it is like mu plus minus. Please check what is the expression for the lambda. Of course.
Mu plus minus j.
Mu plus minus j, right? So j1. Okay, fine. So you see, if mu is greater than 0, it's an unstable focus. That's what I told you. If mu is less than 0, then it's a stable focus.
What about the real part of
The same thing, like we did alpha minus beta, beta alpha. The same fashion.
some of the system we are considering if it is a purely imagination, then it doesn't exist.
Exactly. So from this linearization approach, that is here what we are doing. That is, we are finding the Jacobian means we are like linearizing, and then we are like taking the decision by checking the system, the linearized system. So that will immediately tell if one of the eigenvalues is 0, or in case of the complex conjugate eigenvalues, if the real part is 0.
For only for the pure imagination answer, diagonal.
That means if you have real eigenvalues, suppose if one of them is 0, that is the case of continuum equilibrium points, which we learned in case of LTI. So if it happens in the Jacobian, then it fails. Yes. Then if the real part is 0, in case of the complex conjugate eigenvalues, then also it will fail. So either 0 eigenvalues or complex conjugate eigenvalues with 0 real part. In all those cases, we cannot take the decision about stability from the Jacobian. And that is the reason why, that is, I have converted it into the polar coordinate. And you see, that is, in this whole approach, we are going to do the same thing, that is the stability analysis, but not from the Jacobian. Here, that is, we are dealing with the original system without discarding anything, right? That is the difference between the Jacobian approach and this one. So that is the reason why last day I mentioned that is, this is a highly coupled system. So here, that's maybe from the Jacobian we will be able to do something, or then that is finally the conjecture. I am not saying that there is going to be wrong, it will be true, but you can never get the actual picture of the original system, because here it is like highly complicated. Not only complicated, the complicacy arises because of the coupling. So in all the other cases, like if you see from example 1, for this saddle node bifurcation, transcritical, even after that the pitchfork, it is everywhere the type of the system we dealt with, it is a mostly decoupled system, and also those kind of bifurcation, they are classified as if the bifurcation without any complex conjugate eigenvalue. That's why those are the easier cases. I will emphasize this fact once more, don't worry. But the home bifurcation in one of the cases, or that is a very particular case where it encounters complex conjugate eigenvalues, and then the bifurcation is in the sense when mu crosses the boundary, that means the 0 value. So here the bifurcation means we have to first see that is what happens for mu less than 0, and then what happens for mu greater than 0. Now if you go back to all previous 4 examples, in none of them we had a complex conjugate eigenvalues. Everywhere they were real eigenvalues, and as mu migrates from the positive to negative region or negative to positive region, the stability property, of course, they changed, but never we had complex conjugate eigenvalues. So the change of the stability properties were either from stable node to saddle point or from saddle point to stable node, right? In all those cases, the eigenvalues were real. Please be careful about that. If you check the earlier 4 examples, in all cases of saddle node, pitchfork and transcritical bifurcation, that is wherever there was a change in stability properties, it was either from stable node to saddle point or saddle point to stable node. In none of those cases, we had a complex conjugate eigenvalue. But this is for the first time you see the Jacobian has a complex conjugate eigenvalue. And here the bifurcation is in the sense that is if mu less than 0, it's a stable focus. At mu equals to 0, we don't know what is going to happen. We have to analyze that. But for mu greater than 0, it is going to be an unstable focus. This kind of bifurcation is called a Hopf bifurcation. Okay? Is that point clear? So this is the first type of bifurcation where we have encountered a complex conjugate eigenvalue. And from the bifurcation point, either the stable focus turns into unstable focus or unstable focus turns into stable focus, right? This is a very, very important difference between among Hopf and the other one. Please mention, note it down. This understanding would be really required for like solving the problems. I will draw the bifurcation diagram, don't worry. All of you check my derivation, the previous example, and also try to understand. I will describe the whole thing, don't worry. But first, you must be confident about what we are doing at this moment, at least about the derivation. And also why we, in this case or in such cases, we are compelled to go to the polar coordinate. That might also be a question. That is, earlier that is we handle most of the things in the Cartesian coordinate only. But this is the first time that we are moving into we are just migrating into the polar coordinate. Why that is required? Is it only for some extra analysis, or like this is really a required thing? This is really a compulsion without which we cannot take the decision. What do you think that is why this conversion into the polar coordinate is required, or rather in this case it is indispensable? For all of you, if I ask you that is what are the reasons that is why that is we are required to migrate into the polar coordinate, what would you answer? No, complex eigenvalue, that is fine. That is for a particular situation. But why can't be the analysis will not why can't be the analysis complete in the Cartesian domain only?
It's a couple of systems that is highly coupled.
System is highly coupled, but for that, what problems we are facing?
Because of the complex eigenvalues, we cannot conclude like if it is a stable focus or unstable focus. But by seeing the polar coordinates, if R is increasing and like as we have done in the last one example, we can say
Here, that is from the Jacobian, when you have this one, from that, this stability analysis, this is fine. That is for mu less than 0, it's a stable focus, and for mu greater than 0, it would be an unstable focus. This is fine. But the problem lies somewhere else. Where? That is one of the point that is here. There might be a limit cycle, but which at least at this moment is not possible for us to find out. That is one reason. Another, for completing for the sake of full analysis, that is here. There is a point that is where we will get stuck. That point I am trying to find.
So to find out the region of the transition of the
There we don't have any problem because here we have only one bifurcation parameter mu. So for mu less than 0 one time, for mu greater than 0 another time. That means here at least no change of number of equilibrium points. We have only one equilibrium point, 0, 0. So there is a change in stability properties. Okay. So that's why that is not a problem. The problem is here, since this system is highly coupled, you don't have any idea about what will be the final shape of the trajectories x1 and x2. That's why we are not able to draw the bifurcation diagram. If you don't convert it into the polar coordinate, we won't be able to draw the bifurcation diagram. Are you getting? That is here from these examples, that is up to stability analysis, it is fine from the Jacobian, but still that is the main problem is that you cannot readily find out the shape of the x1t and x2t. And if you don't know that, how you draw the bifurcation diagram? That's a problem. Because bifurcation diagram is x versus mu, or rather x star versus mu. So from this Jacobian, that is we can do the stability analysis, and this will, that is a few times, that is you asked, that is like what is the requirement of H-plane analysis. This is one of the best example where you can see that is we are concluding the stability without solving the original nonlinear equations, right? Which you asked, even Fayaz also asked a few times, that is in the what is the requirement of H-plane. You see that is here, at least for this concluding the stability at the equilibrium point, although they are, please note that all of them are local stability, whatever we are discussing they are local stability. At least for that you don't have to solve the original nonlinear differential equation, right? So that is the beauty or the main utility of H-plane analysis. But when it's a matter of bifurcation, then we need something more, which may not be readily possible for us to find out the solution of x1 and x2. And if we can't do that, or if we don't have that information, then we cannot draw the bifurcation diagram. Maybe from experience you may be close to the original one, but still if somebody asks you that is okay, you perfectly show me the mathematical equation by which you are going to draw the shape, then we are handicapped. But for this stability analysis, this is fine. But here, please note that here also we would have been got stuck if the mu equals to 0. That is immediately now, suppose in the question, in the mixen, which is a very probable question, that is you analyze the stability for mu equals to 0. Now you see if mu equals to 0, what happens? That is originally, from that what will happen? That is it will be like a center case. But as you know, that is if it is a center case in the Jacob for a nonlinear system, it is inconclusive. Then how would you decide the stability for mu equals to 0? That you have to think. And even in that case also, from the Cartesian coordinate, it would be difficult for us to take the decision. You put mu equals to 0 here. It doesn't simplify much, isn't it? If mu equals to 0, simply x1 into minus of x1 minus x1 square into minus x2 square. Similarly here also, if you put mu equals to 0, this doesn't simplify much. So if you have to analyze the stability, then Jacobian method doesn't work because it ceases because of the mu being 0, you are getting eigenvalues with 0 real part, and here the nonlinear differential equations, they are still coupled. So that is also next to impossible for us to get the exact solution for the x1 and x2. There also, that is this, if you convert it into the polar form, then that r and theta will help you to decide. Is it now clear for all of you? So please remember that is whenever we have this tuple type of nonlinear equation, then most of the cases we try to escape to the polar coordinate to get some more techniques, or to be like the same reason for that is why we go to Laplace domain from differential equation. For LTI system, that is one usual question, right? That is, you have a, like say, an nth-order differential equation, and then from that, like what is the necessity that we convert into the frequency domain? Because when you convert into the frequency domain, then you get a transfer function, and there, like most of the cases, the calculation are on the algebraic equations rather than differential equations, isn't it? Because when you have the like nth order numerator polynomial, nth order denominator polynomial, then you are going to find out the roots of some polynomial. So this is mostly algebra. But if you stay in the time domain, then it's a matter of solving the differential equation. That is one of the big advantages in the frequency domain, right? What is the second advantage in the frequency domain? One of the biggest advantage?
Convolution.
Exactly, very good point. Convolution becomes simple multiplication. Yes. So for those kind of results, we migrate into Laplace domain. Here also the same analogy. That is, if you still stay in the time domain, it's about the solving nonlinear coupled differential equation. But if you go to the polar coordinate, then using most of the cases you will find that is they are not only decoupled, but from looking at the expression, you can find out whether r is continuously growing, like increasing or decreasing, or like it depends on something else, like increasing, decreasing. So if you see my hint where I wrote that whether r is monotonically increasing or decreasing, then no question of limit cycle. Can anybody justify that is whether I have written it correctly or not?
If it is not monotonically increasing, or maybe at some point.
Last day, whatever I discussed for limit cycle, just try to remember that and then you try to match with this. Here I wrote if it is monotonically increasing or decreasing, then no limit cycle.
Sir,
If-
the amplitude of oscillation has to remain constant. If R is increasing, then in polar domain system, R increases the amplitude of the
Limit cycle means ultimately it will be a sustained oscillation. And if it is a sustained oscillation, R has to come to a constant value, right? Initially, the value, initially R can be quite large, it may be quite low. If it is low, then gradually it will increase and then leave into oscillation. If it is high, then gradually it will reduce and then that is come back to the oscillation. And after this reaching the sustained oscillation, R cannot change. So that's why if your R dot expression is like that, where the R of t, it is continuously either increasing or decreasing, that means there is no question that there the reaching a sustained oscillation is next to impossible, isn't it? You just check the diagram, like the limit cycle diagram which I drew last day. If it starts from a high initial value, then first there will be a positive damping. So gradually the R will be reducing and then that is it comes to the amplitude of the oscillation. So it comes to R star. Okay. Same thing, if R starts from a low value, then the damping will be negative. So the amplitude of oscillation will grow with time, till it reaches the sustained oscillation, right? So if you have a R dot expression where the R dot changes its sign, then there is a possibility of limit cycle. Are you getting what I am saying? Changes its signs means sometimes it will be increasing and sometimes decreasing. Then there is a chance of oscillation. But if R dot is either positive for all t or if it is negative for all t, that means RT is monotonically increasing or decreasing. Then there is no question of limit cycle. Are you getting my logic? Once again, that is if R dot greater than 0, then what happens? That is RT will increase, right? And if R dot less than 0, then RT decreases. The first one, it is called monotonically increasing nature. The second one is called monotonically decreasing nature. So in that case, there the limit cycle won't exist, right? That means the possibility for forming limit cycle won't occur. Yes.
But at some point, RT equal to 0 because it is going to be increasing. What happens?
That is if it happens, that is suppose like after some time, that is R dot becomes completely equals to 0, R becomes fixed, then it's a different case. So yes, that is also a good point. That is suppose if it happens, that is okay, it was monotonically increasing, or here see what I said, that is monotonically increasing or decreasing. Okay, now that is either always positive or always negative. I never wrote R dot equals to 0. That's why by change of sign means that is somewhat you need that R dot equals to 0. That's why you see that is here I am trying to find out that R dot 0 gives you 2 orbit. That is the thing I wanted to mean. That is for a sustained oscillation, that is you need to have a fixed R. Sustained oscillation means for that the amplitude of oscillation initially whatever may be, but once it reaches the sustained oscillation, R must be constant, right? For a particular system, the amplitude of oscillation must be fixed. So for that, R dot should come to 0, and then that 0 must be maintained, right? So there lies the point, that is if your R dot is continuously positive, or if it is continuously negative, would you ever get that situation when R dot equals to 0? That is the point. So that's why that is here. After that I did the same thing, that is I was trying to find out whether like R dot 0 it exists, like it is possible under this case, and I saw yes it is possible, like if R equals to 0, that is a trivial solution. If R star equals to 0, that's a trivial solution, but it is all the 0 radius. 0 radius means as if it is on the origin. Okay, so that is one possibility, but that's a trivial equation, trivial solution. The other one is the plus mu. That is, I am crossing this one because since it is a radius, we cannot consider the minus root mu. So R equals to plus root mu. That is a fixed radius, right? So there is a chance of limit cycle. In this way we can find out, okay? Although we have the like theoretical means like Poincare-Mendelssohn theorem with some criteria, we will learn those things later, but in this way also, that is we can predict that one, the existence of the limit cycle. Now from this we have to find out that what is the stability property. So if this, suppose this function is f of r, now you find del f del r and then check the stability. So now we are going to check the stability with respect to polar coordinate. If that is fr, then what is your del f del r? Del f del r is your mu minus 3r square. Del f del r, what would be the stability property? So del f del r at r star equals to 0, it will be how much? Simply mu, and del f del r at r star equals to plus root mu, what will be that? Minus 2 mu, right? Any doubt?
So why didn't you write the whole Jacobian?
Look, here I have to do with respect to R because I'm just checking that is what is the situation of the change of the radius.
We're not considering the theta.
Theta is already constant.
Yeah. So
Because if you do that, then immediately then when you find the Jacobian, then it will become 0, right?
yeah.
That's why I am not taking 0. And they are not two, there is coupled. That is also one reason.
Because
Here see we are from that we are trying to find out mainly the existence of limit cycle and also about the bifurcation diagram. So when theta dot equals to constant, that means already we have got the hint that there is a chance of periodic orbit. Then after that you have to check whether that r dot equals to 0, whether that is possible to occur or not. As like Kashyap asked, that is if r dot equals to 0. That is one of the most important point to check that whether there at all there is any chance of limit cycle. Okay. So and now that is what we are going to see. That is from this you have two solutions. One is r star equals to 0, another one is this r star equals to root over mu. Right? Now you have to check whether these equilibrium points, of course in the polar coordinate, whether they are stable or not with respect to mu, and from that we are going to draw the bifurcation diagram. Here you see we have already got like now the situation is more or less comparable with our earlier situation, as if one equilibrium point is r star equals to 0 and theta star equals to t. That is one equilibrium point, and the other one is r star equals to plus root over mu comma t. That is my equilibrium point. After drawing the bifurcation diagram, it will be clear. That is first, let me see that is what is going to be the situation for r star equals to 0 and r star equals to root over mu. So r star at the Jacobian at r star equals to 0 equals to mu. So what happened? That is if for positive values of mu, what is the situation? Isn't it? For positive mu, it will give you an unstable focus, and for negative mu, it's a stable focus. Now, is it matching with this? But have you also marked that is we have got another information which was absent here? The existence of limit cycle, like there is a chance that r star equals to plus root over mu. That is that if the limit cycle occurs, and here definitely we have a chance of limit cycle whose radius would be root over mu, but which was completely suppressed or absent in this analysis. I hope now you have understood. That is why converting into polar it is really important for us. Here now you see that is here we had only one equilibrium point 0 0. For that we analyze the stability. For mu less than 0 it's a stable focus, for mu greater than 0 it's an unstable focus. Now you come back here. Now the r star 0 that corresponds to the equilibrium point 0 0, because there it is here. What is the equilibrium point? x1 star comma x2 star. What is your r? R means root over x1 star plus x2 star, isn't it? So r star 0 is nothing but this equilibrium point, and for that we have got the same stability property. That is for mu less than 0 it's a stable focus, for mu greater than 0 it's an unstable focus, right? Exactly the same thing we have got. But this information, the second one, so that is 1, that is 2, is 2. this was completely absent there. Because the moment you follow the Jacobian approach, you are killing the nonlinearities, right? So a huge chunk, almost half of the things is suppressed there.
So here also use the Jacobian.
But I use the Jacobian that is only for checking the, rate of change. It is like here only that is you may not say that it is a Jacobian. It is the only thing that is you have, this is a function that and I am checking the rate of change of R, right? Jacobian means here did I apply any kind of Taylor series expansion? It is not, so that's why in true sense it is not a Jacobian.
Determining the rate of change of the radius, we are not using Jacobian, we are using Jacobian to find the extreme point.
Here you see the Jacobian is in the sense when you were checking this function f of r and then I took del f del r. Somebody can think it as if this is a Jacobian, but truly speaking this is not a Jacobian. Here we are analyzing that if it is a function, then we are trying to find out the maxima minima. Are you getting? Previously that is I portrayed it as Jacobian, but please don't think as a Jacobian, because if you think it as a Jacobian, it may create some confusion. You think about that this is a function and then we are checking the maxima and minima. If you ask that sir, why you are interested in finding the maxima or minima with respect to R, because I am very much interested to check whether it gives a non-zero constant R. That means I am trying to find out that whether there is a possibility of R dot equals to 0 and maintaining R dot equals to 0. Are you getting? That is the condition for limit cycle. Not only R dot equals to 0, maintaining R dot equals to 0. And if you would have the only solution R star equals to 0, that means that is the trivial solution, that never gives you a limit cycle, right? Because if it is a limit cycle, it has to be a sustained oscillation of a R star non-zero R star, right? So R star equals to 0, that doesn't tell you that there is a limit cycle. Of course, you should have got a non-zero R and a positive R of course, because radius cannot be negative. So that huge information you cannot get unless you convert it to the polar coordinate. That's why this conversion is really, really important. Is it now fine for all of you? And what about the stability for that? Again, the stability is in the sense of an one-dimensional coordinate. Once again, could you read it? Last time also I said that is if you have a scalar differential equation x dot equals to mu minus x1 square, then just by checking the sign of sign plus minus sign of x dot, we can find the stability, right? Stability in the sense whether that point is attractive or repulsive in nature. Like suppose you have x dot equals to mu minus x square. So that is how can you find out whether an equilibrium has an attractive nature or repelling nature? X into x dot, it has to be negative. That means if x into x dot is less than 0, that will give you attractive nature or the stable nature. Attractive equilibrium point. Do all of you agree with that? X into x dot less than negative. What does that mean? If x is positive, x dot will be negative. So even if at the beginning x was increasing, but eventually it will decrease and come back to 0. On the other side, initially if x is negative and suppose it was increasing in the negative direction, but now x dot will be of opposite sign, positive, so that negative value will ultimately start reducing and then it will stop at 0. So that is attractive equilibrium point, okay, or the stability with respect to scalar differential equation. That is a very useful technique, but only for the decoupled ones. That technique cannot be applied here because here you don't have decoupled ones. Here all of them are coupled. Once you convert it to the polar form, and that too if it is in the decoupled format, then you can apply all those small tricks. So here that is R star equals to plus root mu. What is the situation? For what is the stability? For mu greater than 0, it's minus, right? So for mu greater than 0, it's a stable. So here it says that if limit cycle occurs, it will be a stable limit cycle. Do you have any accompanying fact which will say you that yes, it will be a stable limit cycle? Or it's one going up. This is a very important question, very interesting as well. That is this for R star root mu equals to minus 2 mu. So for mu greater than 0, it's stable. So it is saying that it should have been a stable limit cycle. Now, do you have any accompanying fact which will speak in favor of this? That is, do you have any additional information which will confirm you in this regard that yes, if the stable cycle or if the limit cycle occurs, it will be a stable limit cycle?
R dot equal to 0.
No, that is fine. R dot equals to 0. From that, how, because limit cycle can be stable or unstable, right? You check the last day, I give 2 figures. For stable limit cycle, what was the nature of the 0, 0 equilibrium point? Check my.
We are getting at root mu into 0 for mu greater than 0, we are getting minus 2 into mu. So if we convert
For mu greater than 0, that is, if you have a like stable limit cycle, and now for the same time, that is for mu greater than 0, what about the stability of R star 0? That's an unstable focus. So do this, like, are they conforming to each other? You check my diagram which I drew last day.
So from 0 it is converting to a limit cycle.
Not, that means actually it is a unstable focus, diverging towards the limit cycle. That is the backup fact. That's what I wanted to mean.
So is it always like that? Stable limit cycle, unstable focus, and unstable limit cycle?
Exactly, otherwise it cannot happen. Stable limit cycle means, of course, you should have an unstable focus. Or if it is unstable limit cycle, then you will have a stable focus. So in that way, you have to check that is what you are doing, whether that is correct or not. So all these analyses are highly required, and these are not written in any of the books.
But how can we confirm that after going outside from the origin, it will stop at the limit cycle? The converging part should stop at the limit cycle.
That's what that is that bifurcation. The limit cycle, if you see the time response, what I drew, that from x01, x02, initially the amplitude of oscillation will be different, and gradually they will reach the R star equals to root mu. That is the point we have got from the differential equation R dot, the rate of change. In that respect, I said that is, if it is continuously positive or if it is continuously negative, no chance of a periodic orbit. So it will be ever increasing or it will be ever decreasing. But if it is sometimes it is increasing, sometimes decreasing, then only you have a chance of getting R dot equals to 0. Highly interesting, all this analysis. And at the same time they are tough as well, because you see that is, we had only those 2 differential equations. From that we have extracted so much of information. So this logical sequence of thinking, that is the most important. Please check yesterday's notes and these today's notes as well, because they are totally linked.
Sir.
Just 1 second.
R star, we got two different nature of mu.
No.
For R star 0,
We are checking the behavior of R star depending upon mu values, because mu is a parameter which is not in our hand. It can be some positive number, it can be some negative numbers. This R, that is the amplitude of oscillation, right?
Yeah. So the first different dou f by dou r, the first one that we got was mu. So for mu greater than 0 and less than 0, we have got one relation. And for
No
next
relation,
and
actually
behavior.
R dot, that is the differential equation, and we are trying to judge that what is the pattern of R of t. In a very simple word, maybe that is you all the remaining students also have the same doubt, that here what we are trying to do. Here simply we are trying to find out the pattern of RT. Again the same thing, that is it's a nonlinear differential equation and we don't want to explicitly solve it. But we need to check the pattern of RT. Why? Because whether if it is continuously increasing, cannot be any limit cycle. If it is continuously decreasing, there also it cannot be any limit cycle. So if it increases, decreases, increases, then there is a chance that is at some point R dot will become equals to 0 and that condition will continue.
So your R of t is basically the amplitude of oscillation that's
And it is not a fixed number, it is R of t, it's a function, right? But here also we still don't like to solve the nonlinear differential equation. Instead, that is we are finding the equilibrium points, what can be the possible values of R if R dot equals to 0. That is whether there is at all any chance of R dot equals to 0. That's what we are finding, the solutions of R dot equals to 0.
So can you explain me this, that if R dot is increasing and sometimes decreasing, in that changing nature, how do we come into a conclusion that at some point it will show you a limit cycle?
Like here, you see that is, suppose that is an initial value of R that is really less. What is R? Root over like x at initially R0. Have you all understood what she is asking? That is, from this, how do you get to know that is, yes, that R can initially it was non-zero, after that somewhat it is gradually coming down to 0. How is that possible? Or intuitively, what the analysis which we are doing mentally, what is the logic behind it? So as you know, that is my R equals to root over x1 square plus x2 square. So what is the initial radius, that is initial condition on R0? That is going to be x10 square plus x20 square. Okay. Now suppose both of them are really very low value. Let's say this is equals to 1 and this is equals to 0. That is I am considering the x0 that is 1 0. Okay. Or maybe suppose it is 0.50. So in that case it will be 0.25. So R0 that will start from the value 0.25, and then so I still don't know that is what will be the solution of this one. So initially you see what will happen, that is like now this mu depending upon mu, that mu into R, that means like mu into this value, it would be either less than R cube or greater than R cube. So accordingly, initially, that is accordingly it will be decided whether the initial slope, that means initial R dot, whether it is negative or positive. Like now suppose the initial R dot, if it is positive, then from this 0.25 it will keep on increasing. That is, if R dot equals to 0 initially, then what will happen? That will imply that RT will increase from 0.25. And if this is the opposite, and then how long it will increase? That is, where is it? How long it will increase? Suppose then when R is increasing, everybody please look into the board. When R is increasing, mu into R it is increasing, right? And then how long it will keep increasing? Till it becomes equals to R cube. The moment R cube becomes equals to mu R, then R dot becomes 0. After that it cannot do anything, and that is the point where it will turns into, or where the limit cycle oscillation starts. And exactly the vice versa. If r dot is less than 0, then that is r3 will decrease starting from r0. So here 0.25, that is my r0. That is the logic. And here we are like trying to find that one only. That is there any chance of occurring r dot equals to 0? So have you seen that is this r star equals to root mu, that is non-zero radius, this whole part, that means this existence of the limit cycle, this whole thing is not possible to come out from the Jacobian analysis, because there we have discarded the non-linearities, and that's why the linear approach, for the linearization approach, although that is very handy for us to do and easy to understand, but it also at the same time it compels to lose many things, right? Now finally we will draw the bifurcation diagram. Okay? Can anybody tell me that is in the r theta coordinate, and of course the mu in the independent variable, what would be the shape of bifurcation?
It is a graph like this.
Like as if a parabola and which is rotating in a uniform velocity. So ultimately it is a paraboloid. I am going to draw, although on a 2D plane it is difficult to draw, but still I am going to try. But first of all, you think about the derivation. Okay, let us take a small break.
क्यों भैया? क्योंकि सर जो पढ़ाते हैं आखिर तक भूल जाता हूँ।
তাও তো আমি এত আস্তে যে পড়াচ্ছি, খুবই স্লো। See, I am the slowest among all the instructors. I hope in your this semester, even the last semester as well.
আপনার সাবজেক্টগুলো কঠিন না?
কি?
আপনার সাবজেক্টগুলো কঠিন না?
Okay, it is. The same diagram, just I'm like trying to draw it in a better way. It would be like that. please look at me. Like this is a parabola, suppose this one. Now, why this is like a little bit difficult to understand this paraboloid? Because here, please don't get confused with pitchfork bifurcation. Because it will give you a feeling this one is there, similarly this one is there, so as if this is like a pitchfork bifurcation. No, it is not. Here you don't have r star equals to minus root over, that one is not there, right? Because this is not the x1 star, x2 star, it is r star cannot be minus root over mu. So here what happens, that is r star equals to root mu, that is the solution of the r, of course, but there the theta dot equals to constant, that means it has an angular velocity. Now that is, suppose like for mu, if mu equals to 1, then what happens, r star equals to 1, so the amplitude of sustained oscillation is 1. Now that is, if it is that r star, that is amplitude is constant, but it is like a phasor, right, which is continuously rotating at a constant velocity. So it is like, please all of you look at me, like this. So that's why it is like a paraboloid. Are you getting? Once again, like if you see exactly the same shape, but now that will keep on rotating like that. And why all these intermediate lines? Because I don't know what is the exact value of mu. It can be only this much, it can be this much, it can be this much. Because you see, x-axis is the mu axis. That is the manifestation. This is the supercritical. Now the other one is subcritical. Why this is subcritical? Because there you will find that is in one side there is no stable equilibrium point or limit cycle, whatever you call it. But please check the diagram from the book once, because I don't exactly remember. This one I am quite sure. For subcritical, this is the shape roughly would be, but about the stability properties. I believe that it would be unstable on this side. And the other diagram which I was talking about, if the initial condition, suppose this is a stable limit cycle. Stable limit cycle means that is it will attract all the nearby trajectories, right? So if you have an initial condition here, maybe it will go like this. If you have an initial condition here, maybe it will go like this. Here arbitrarily I am putting the direction, okay, that I don't know which side it will go. If it is like there, then maybe also it will go like this. Now, if it is inside, then always it would be a logarithmic spiral outward. Why? Because that we have seen from the Jacobian. If you see what were the eigenvalues, so lambda of j, that was mu plus minus j1. So for mu greater than 0, it's an unstable focus, right? So that is. So for mu greater than 0, it's an unstable focus. So like this. If it is suppose here, then also are you getting? So this is the case of stable limit cycle. So that's why I said, if it is a stable limit cycle, you must get an equilibrium point at the center, which must be unstable focus. And similarly, had it been a unstable limit cycle, then that would act as a repeller. So then the 0 point would be a stable focus.
Sir, here the shape of the limit cycle. Why did
I have done it arbitrarily because I don't know finally how does it look like. Certainly, the center, the PO circle case is very limited because it is with respect to the original nonlinear equation. So they are getting a perfect cycle is next to impossible. That's why I am drawing like this. It's like a closed curve. Unstable cycle.
Sir,
Hmm.
sir, the direction of the spiral of the unstable focus, should it match the sense of rotation of the limit cycles? So because in this case,
That I cannot readily say because ultimately the direction that is has to be ascertained from that dz2 by dz1 from that. Most possible that is it will be the same only, but it may not be. That is I am not 100% sure. Anyway, I will also check because whenever that is we try to see that which one how the direction, then that is we have to always consider that equation, that what is the sign of dx2 by dx1. Like when we follow the method of isocline to draw the phase plane diagram, from that everywhere you will be getting the tangent along with the sign. At this moment I am not using that isocline method, so that's why you are getting little bit doubt about the sign. But if you draw it following that, immediately at the very beginning only the sign will be clear. I am giving you two more practice problem. Limit cycle we have more or less discussed with respect to examples. Only thing that is you have to verify those things from book. Okay. A method of isocline, you see in the the slot-in book, they have taken the example of Van der Pol oscillator and they have given the full diagram, that is how to draw the phase plane diagram using the slope. Okay, please check that one example, try to do it by closing the book, that only one example and the concept is fine. Method of isocline is nothing, it is when you have that x1 dot equals to f1 something, that is for any of the two-dimensional system, suppose x1 dot equals to f1 of this, x2 dot equals to f2 of this. Now that is always the slope matters, because if you have to draw the phase plane, you need the slope. So the slope means, now if you divide this one by this, then of course dx2 by dx1, that is going to be f2 by f1, that is nothing but a vector field. From that the direction comes, that is everyone, that is we are discussing about, talking about the direction. So this is a vector field, and from that the question of direction comes. So from that in the slotting book, that is very easily they have solved the example of Van der Pol oscillator and they have shown that is how to draw the phase plane, considering slopes at different locations. Okay. Tomorrow morning's class is cancelled because I have an urgent meeting at the admin building. In between, if you have any doubt, any other thing, feel free to ask me. You post on the our WhatsApp group, no problem. And whatever I have taught in the class, that is the syllabus. Okay. Practice it well. That is from bifurcation, you can expect one or two problems. It is mostly about that is how you handle. Now, suppose say for example in such cases, it may apparently they seem to be tough, but they are not at all tough, because finally you are going to either convert them into polar coordinate, or the first step is you have to find the Jacobian. Jacobian means del f del x. So although the equation they looks like complicated or a little lengthy, but once you find the del f del x, most of the times will get cancelled out, and especially after putting the equilibrium point. So for any of the phase plane analysis, the first step is you find out the equilibrium points, second step you find out the Jacobian, then third step is you substitute the value or find the eigenvalues of the Jacobian at those equilibrium points, you go for the stability analysis, and finally if it is a bifurcation problem, then you draw the bifurcation diagram. Now if you have a coupled system, you may need to convert it into the polar coordinate. Okay, so these are mostly 5 or 6 steps. What are the other things we did? So at the beginning, that is, we had a lot of discussion about the difference between linear and non-linear systems, and the foundation also we did something on uniqueness, convergence, uniqueness, existence, right? Can anybody please remind me of the topic which we discussed? Because chaos we didn't judge, right? Lipschitz I didn't discuss, right? So after that we have but Lyapunov also I didn't discuss. Okay, thank you. But Lyapunov तुम लोगों का पता है ना?
प्रॉब्लम
How to solve the problem, that is not.
वो भी बताया ना,
Non-linear. Okay. Okay, in between if you have any doubt, please feel free to